Imagine a colossal storm brewing, not in the atmosphere, but in space, hurtling toward Earth at millions of miles per hour. What if, in 2025, a massive solar storm strikes our planet? Could our modern technology withstand the force of nature's most powerful tantrum? Solar storms, also known as geomagnetic storms, occur when bursts of energy and charged particles from the sun slam into Earth's magnetic field. These events can disrupt satellites, GPS systems, power grids, and communication networks, integral parts of our daily lives. The most intense solar storm ever recorded happened in 1859, called the Carrington Event. Telegraph systems failed, and auroras lit up skies as far south as the Caribbean. Scientists warn that a similar event today could cause widespread chaos, given our reliance on technology. Why should we care about solar flares, coronal mass ejections, and solar maximum cycles? How do these phenomena connect? What can we expect if such a storm hits again? Researchers around the world are studying these questions, developing early warning systems and strategies to protect our infrastructure. Think of Earth's magnetic shield as a fragile glass dome, brilliant but vulnerable. A powerful solar storm could crack that dome, shaking the foundation of our digital civilization. Not with thunder, but with invisible waves of energy. Welcome to this deep dive on solar storms, where science meets the urgent realities of our interconnected world. Let's explore what the coming years may hold and how close we might be to another Carrington-level event. Comparison with the 1859 Carrington Event. Let's travel back to the year 1859, a time long before smartphones, satellites, or the internet. That year, a powerful solar storm struck Earth, now known as the Carrington Event. It remains the most intense space weather event ever recorded in history. Imagine living in a world where the telegraph was the fastest means of communication. During this event, telegraph systems across Europe and North America failed spectacularly. Operators received electric shocks, and some telegraph machines even caught fire. Messages were sent with the power off because the storm itself induced electric currents strong enough to operate the equipment. At the same time, dazzling auroras appeared in the night sky, visible not only near the poles, but as far south as the Caribbean and Hawaii. These northern and southern lights, usually rare at such latitudes, painted the sky with brilliant colors, leaving many in awe and some in fear. But the Carrington Event was more than a dazzling natural light show. It caused widespread disruption of communication systems, throwing entire regions into isolation. Though the world was less dependent on electricity then, the effects were still dramatic and dangerous. Fast forward to today. Our civilization's reliance on electricity and digital technology has grown exponentially. Power grids span continents, satellites orbit Earth providing GPS and communication, and billions depend on these invisible systems every day. A solar storm, similar to the Carrington Event, now poses threats, not just to telegraphs, but to vital infrastructure that supports modern life. Beyond Earth's surface, satellites face immense danger from charged particles that can damage their electronics or disable them altogether. GPS navigation, crucial for everything from transportation to military operations, can become unreliable or fail during severe space weather. Moreover, intense solar storms may even affect human health, with increased radiation exposure for astronauts and high-altitude flights. Economically, the consequences could be staggering, potentially costing trillions in damages and downtime. This historical event serves as a stark reminder. the power of the sun is both life-giving and potentially catastrophic. Understanding the Carrington Event helps us grasp the scale of the challenge we face as we enter a period of heightened solar activity. Next, we will explore how these solar storms specifically threaten satellites, GPS, and our broader technology systems. Impact on satellites, GPS, and technology systems. Think of satellites as the nervous system of our modern world. Any disruption sends shockwaves through countless connected devices and services. Building on what we learned about the Carrington Event, let's dive into how solar storms specifically threaten these vital technological lifelines. Under normal conditions, satellites orbit Earth, quietly transmitting data that powers everything from navigation apps to weather forecasts. GPS signals guide planes, ships, and even your daily commute with remarkable precision. Communication satellites keep us connected across vast distances. But when a strong solar storm arrives, this delicate balance can quickly unravel. One of the most visible effects we can observe during intense solar activity is the sudden appearance of bright auroras, nature's spectacular light show. However, behind this beauty lies a turbulent assault on our technology. Charged particles from the sun interact with Earth's magnetic field and atmosphere, creating disturbances known as geomagnetic storms. These storms can induce electrical currents in satellite circuits, causing temporary malfunctions or even permanent damage. Imagine your smartphone suddenly losing GPS signal in the middle of a city because the satellite guiding it is being scrambled by solar energy. This interference can lead to navigation errors, dropped communications, and disruption of critical services. Scientists explain this phenomenon using the concept of space weather, where solar emissions impact the near-Earth environment, much like a storm affects the Earth's surface. When satellites are hit by high-energy particles, their electronic components can short-circuit, sensors may become unreliable, and onboard systems might reboot unexpectedly. In calm times, satellites operate smoothly, protected by engineering safeguards and Earth's magnetic shield. But during severe solar storms, these defenses are overwhelmed. The difference is akin to a quiet, well-functioning city suddenly plunged into chaos by a massive power surge. Importantly, the impact is not permanent. After the storm subsides, satellites undergo a recovery cycle, returning to normal function, though sometimes with lasting damage that shortens their operational lifespan. Similarly, GPS signals regain stability, but repeated exposure to strong solar storms poses ongoing risks. Understanding this cycle helps researchers develop better prediction models and protective technologies. By monitoring solar activity and geomagnetic conditions, agencies can issue warnings and temporarily adjust satellite operations to minimize damage. As we continue, let's explore the heart of these solar disturbances, the X-class flares, and examine the real data from 2025 that could signal the approach of a new era of intense solar activity. X-class flare, definition and 2025 data. Let's explore what an X-class solar flare is and why it matters. Imagine the sun suddenly unleashing a colossal burst of energy, like a powerful cosmic storm blasting across space. This is what happens during an X-class solar flare, the strongest type of flare our star can produce. Solar flares are intense flashes of radiation caused by the sudden release of magnetic energy stored in the sun's atmosphere. They come in different classes, ranked by their X-ray brightness. The smallest flares are A-class, barely noticeable, while M-class flares are moderate storms. But X-class flares, they are the giants, capable of unleashing energy equivalent to billions of atomic bombs exploding at once. During an X-class flare, magnetic fields in the sun's atmosphere twist and snap, releasing energy that accelerates charged particles and emits intense radiation across the electromagnetic spectrum. This radiation can reach Earth in just 8 minutes, the time light takes to travel from the sun, impacting our atmosphere and technology almost instantly. When an X-class flare erupts, it sends waves of high-energy particles and radiation hurtling toward Earth. These bursts can disrupt radio communications, interfere with GPS signals, and even cause power grid failures if strong enough. What makes X-class flares particularly significant is their potential to trigger severe geomagnetic storms. Unlike smaller flares, their sheer power can overwhelm Earth's magnetic shield, leading to widespread technological disruptions. In 2025, scientists have recorded several notable X-class flares, marking one of the most active solar periods in recent decades. Data from solar observatories shows a rising trend in both the intensity and frequency of these flares. This uptick raises concerns about the increased likelihood of a Carrington-level event, an event of extreme severity that could challenge our preparedness. While exact predictions remain difficult, these observations underscore the importance of continuous monitoring. Advanced satellites and ground-based instruments track solar activity in real time, helping experts issue warnings and coordinate protective responses. On the positive side, understanding X-class flares enables early warning systems, giving power companies, satellite operators, airlines, and emergency services precious time to prepare. Protective measures might include temporarily shutting down vulnerable systems or rerouting flights to reduce radiation exposure. Yet, despite advances in solar science, the risk of sudden, unpredictable flare events persists, reminding us of our technological vulnerabilities and the need for resilient infrastructure. To put it in perspective, imagine the sun's surface as a boiling pot. Smaller flares are the bubbles that pop occasionally without much fuss. X-class flares are like massive eruptions that send steam and heat surging far beyond the pot, reaching Earth with potentially serious consequences. This powerful phenomenon, while awe-inspiring, demands respect and preparation. As we delve deeper, the question remains: how does this intense solar activity fit into the broader cycle of the sun's behavior? Next, we'll examine the solar maximum of 2025, when solar activity peaks and the stakes are highest. Solar activity cycle peak, solar maximum 2025. Now, let's understand the solar maximum expected in 2025 and why it matters. The solar maximum is the peak phase in the sun's approximately 11-year activity cycle, characterized by the greatest number of sunspots and increased solar eruptions. This cycle profoundly impacts our planet and the technology we depend on every day. To picture this, imagine the sun as a boiling pot of water. During the solar maximum, the surface bubbles vigorously, with numerous sunspots appearing. Dark, cooler regions caused by intense magnetic activity. These sunspots are like hotspots signaling where energy is about to erupt. Alongside the increase in sunspots, the sun releases more solar flares and coronal mass ejections, powerful bursts that can send charged particles racing toward Earth. This heightened activity can disrupt satellites, power grids, and communication systems. Scientists track these changes using advanced instruments both in space and on Earth. One key player is NASA's Solar Dynamics Observatory, SDO, orbiting our planet and providing real-time images of the sun's surface in incredible detail. It captures solar flares, monitors sunspots, and measures solar radiation levels. Another vital tool is the Parker Solar Probe, a spacecraft launched to dive closer to the sun than any before. By gathering data on the solar atmosphere and solar wind, it helps researchers understand the forces driving the solar maximum. Ground-based observatories also contribute, using solar telescopes equipped with special filters to study sunspots and magnetic fields. These observations are essential to build accurate models predicting solar storms. Looking back, previous solar maximums have varied in intensity. Some cycles brought mild increases in activity, while others, like the one leading up to the Carrington Event in 1859, were extraordinarily violent. The 2025 solar maximum is expected to be moderately strong, but with enough power to challenge modern technology. Understanding the dynamics of this cycle enables scientists and engineers to prepare and protect critical infrastructure. By combining satellite data, solar probes, and ground observations, they create forecasts that help mitigate risks. This continuous monitoring and research represent humanity's growing ability to coexist with our star's moods, turning what once was unpredictable into manageable knowledge. As the solar maximum peaks, unexpected phenomena can emerge, such as auroras appearing far beyond their usual regions. Next, we'll explore these unusual auroras lighting up states where they are rarely seen, revealing more about the reach and power of solar storms. Auroras appearing in unusual states. Imagine seeing the auroras lighting up skies far beyond their usual northern boundaries. In recent months, this breathtaking phenomenon has surprised many by appearing in U.S. states where such displays are rarely, if ever, seen. Typically, auroras, also known as the Northern and Southern Lights, are confined to high-latitude regions like Alaska, northern Canada, and Scandinavia. These dazzling light shows occur when charged particles from the sun interact with Earth's magnetic field and atmosphere near the poles. However, recent reports have documented vivid aurora sightings in southern states such as Texas, Georgia, and even Florida. This unusual expansion signals a significant and intense period of solar activity affecting Earth's magnetosphere in ways not often observed. So what drives auroras to appear so far from their usual zones? The key lies in the behavior of the sun during active periods, especially when it emits large bursts of charged particles during solar flares or coronal mass ejections. These solar storms send streams of energetic particles toward Earth, where they collide with and disturb the magnetosphere, the protective magnetic shield around our planet. When these disturbances are strong, they compress and deform magnetic field lines, allowing charged particles to funnel into the atmosphere at lower latitudes, creating auroras in unexpected locations. To monitor and understand these events, scientists use a network of satellites equipped with magnetometers and particle detectors that measure changes in Earth's magnetic field and solar particle flux. Ground-based observatories with sensitive instruments track the position and intensity of the auroral oval, the ring-shaped zone where auroras typically occur. Together, these tools form a comprehensive space weather monitoring system. Agencies such as NOAA's Space Weather Prediction Center analyze incoming data to forecast geomagnetic storms, providing early warnings that help utilities, satellite operators, and airlines prepare for potential disruptions. For example, power companies can adjust grid loads to prevent damage from geomagnetically induced currents, while airlines may reroute polar flights to avoid increased radiation exposure during intense solar events. Despite the beauty and intrigue of auroras appearing in these southern states, they also serve as reminders of the underlying risks. Increased geomagnetic activity can disrupt communication systems, impair GPS accuracy, and cause voltage fluctuations in electrical infrastructure. Yet, scientists stress that not every aurora sighting at unusual latitudes equates to a disaster. Forecasting models consider multiple variables, such as solar wind speed, magnetic field orientation, and particle density, to gauge the severity of each event, ensuring measured responses rather than alarmism. The ongoing research and technological advancements represent humanity's commitment to coexisting safely with our dynamic star. Continuous improvements in satellite instrumentation, data analysis, and communication networks are vital to maintaining resilience against solar-induced disruptions. As we witness auroras painting skies far from their traditional homes, we're reminded of both the sun's immense power and our growing ability to understand and adapt to its influence. Next, we'll conclude by reflecting on the broader implications of these phenomena and how knowledge equips us to meet future challenges calmly and confidently. Stay informed about solar activity to protect your devices and support community preparedness. Knowing when solar storms are approaching allows you to take simple steps like unplugging sensitive electronics or adjusting travel plans to reduce potential disruptions. If you found this video helpful, please like, share, and subscribe to stay updated with the latest space weather news. Your engagement helps spread awareness and keeps our community ready for whatever the sun might send our way. As we've seen, solar storms are complex but not unstoppable. The combined efforts of scientists, advanced satellites, and early warning systems work tirelessly to monitor the sun's moods. These tools analyze solar flares, sunspots, and geomagnetic shifts in real time, giving us the best chance to prepare and respond effectively. Remember, while the sun's activity can be powerful, it is also predictable to some extent. This balance between understanding and caution allows us to live confidently under our ever-changing star. Thank you for joining us on this journey into solar science and space weather. Stay curious and stay safe. Next time, we'll dive deeper into how solar storms affect human technology and what innovations are being developed to shield us from their impact. Don't miss it.